All right. I got some wisdom for the kiddos.
Okay.
If you, students, have not had a glass of water today, you must pause the video now and go get a glass of water. Hydrate or dihydrate.
Wow. It's a lot.
Also, go Terps.
Go Terps.
Always time for go Terps. Like I got my Terp gnome. I actually took down my my flag. It was a little obnoxious.
What? I don't know. I don't think Maryland flags are obnoxious.
It's right here. I guess I could wear it as a flag, as a cape. Oh wait, no. Wait, no. Does the denominator wear a cape? We know that the reciprocator
dresses like a pirate.
You're right.
The denominator
and does not wear a cape.
Capes.
Yeah. And is green.
Mm-hmm.
All right. I don't want this video to get too long, but let's jump into it then. You ready?
Jump.
Awesome. So before we get started, is there anything that you need so that you can help me in this doc?
Well, I need access to the dot. Can you click on the triple like less than sign, triple dot less than sign to share that doc with me?
Boom. Where is the share in the triple?
It's the less than sign.
Dot.
Yeah, triple
yeah,
dot.
so it's like a dot that's being split into two dots.
Yeah.
What's that? What is that in biology?
Bifurcate.
Ah, yes. I guess. I don't know.
I don't know. Budding? Is it budding? Splicing?
I was gonna say like mitosis or meiosis or something. I don't know. Anyways, I'm dropping it in the chat right there. You have access now. The important thing here, everyone, is that we're using this share link and not the URL that comes with the web page, because that will not grant people permissions to edit. All right, let's do some basic trigonometric identities.
Wait, Mr. Kirk, can we widen?
Yes, we can.
Zoom in. Can we zoom in? That's what.
Full width. Words. Yeah.
Full width.
With what I was saying, though, thank you for pointing that out. Trigonometric identities, basic ones. We're going to get a lot later. There's an entire unit about trig identities, but we want to get the basics ones so we can finish up the basics of trig. What is an identity? What does the Google say?
What does the Google say?
What does the Google say?
I can spell identity. It looks like it was a film. Identity. No, identity. I spelled identity wrong.
Fair enough. Make sure you get the mathematical definition. We don't need like who you are.
A transformation that leaves an object unchanged.
Ooh,
or
perfect.
The equality of two expressions for all values of the quantities expressed by letters, or an equation expressing this.
Awesome. So wait, what that tells me is 2x equals 1. That's not an identity.
Okay.
Because there is one value that makes that thing true. However, x is equal to x, that's an identity. No matter what value, for all values on our domain, that thing is a true statement. So as we proceed, that's what we're doing here. We're not solving equations today. We're looking at equations that are identical, and we're verifying that they're true, or just coming up with identities that are true, not necessarily even verifying. That's what we're doing here. We got some identities that we've already got in the pocket. We got the reciprocal identities. Sine and cosecant are reciprocals of each other. Cosecant and sine are reciprocals of each other. What did I do about 20 minutes ago, Mrs. Contreras? You and I were doing some math together. What mistake did I do in regards to this word?
Oh, reciprocal. Oh, you said inverse, and I got kind of annoyed and said, no, Mr. Kirk. Sine and cosecant are not inverses. They are reciprocals.
Mm-hmm. And I think that's an important thing to like bring up. And we've already started to use inverses as well. Like we've started to solve equations like sine theta is equal to 0.2. We've been using the function in the calculator, the inverse sine function. It's not the reciprocal. Right? That symbol to the -1 is a very confusing symbol, I might say. because it's used all over the place to mean different things. But in the calculator, when you use that inverse symbol, that -1, that's referring to the inverse, not the reciprocal. It equals something. I forget what it was. I think it equals like 0.201. Anyways, we got our reciprocal identities. We got our quotient identities. And these are all written out for you guys. You have access to this document. So we got a little place that all our identities are going to slowly be collected. We have the symmetric identities. Tell me some stuff about this, Mrs. Contreras.
Well, this is because we have even functions for cosine and our reciprocal of cosine, which is secant, and then we have odd functions for our sine and our reciprocal of sine, which is cosecant. And with our tangent and our cotangent, those are odd, because when you put in the opposite, you get out the opposite.
Mm-hmm. And now that we've graphed cosecant, no, we haven't graphed cosecant and secant and cotangent or tangent. We've graphed sine and cosine, and those things are odd. Sine looks like that, and then it continues. Cosine looks like this, and it continues. And those are even and odd as we visually remember them. And then last but not least, the cofunction identities. So really we have 6, 12, 14, 20 identities already in the pocket. And hopefully you have these memorized. Hopefully that didn't require any effort.
Or you have them written down somewhere that's easily visible that you can look at often. Something like a poster.
I should put like a poster behind me. Anyways, I would argue that these they all kind of make sense and we're starting to internalize them. Let's get some more. And these ones are, by some people's standards, their favorite. Oh, you fucking crap. Oh, you're purple like my shirt. That's awesome. All right, so I'm going to destroy
your purple? It looks blue.
So. It is purple.
Oh, my shirt.
It's purple, right? It's totally purple. I have my what is it called?
Producer.
My producer, yeah. All right, so we have all these identities.
I'm erasing the crab so that we can.
Because we will need that space, yeah.
Yeah.
That's a very detailed crab.
Thank you. It's because we're talking for an entire page and I didn't have to do anything.
Yeah. All right, so I'm going to zoom out a little bit. I know you wanted to keep it zoomed in, but we want to be able to see this whole thing. All right. I want to try to discover some more identities, equations that are true regardless of what you plug into them. So hopefully this geometric scenario will reveal some more identities. What do you see all over the place in this geometric picture?
There's a lot of letters.
Okay.
There's a lot of triangles.
Triangles.
And there's part of a circle, so that I guess gives us different radii.
Okay. So we have lots of letters to be able to describe what we want to describe. We have lots of triangles. Before we move on from the triangles, what kind of triangles?
These are all right triangles.
Right triangles. Right triangles. Yeah.
Right angles. I guess this one doesn't have a right angle, but we know that it's going to be a right angle on that side.
Yeah, because this is a line right here. Yeah. Mm-hmm. All right. So, and then you said one other thing. There's a circle here, and so there's going to be some congruent radii appearing. We have one of our radii labeled BD.
Oh, nice. It's 1. So we have parts of like a unit circle.
Unit circle. Cool. All right. What else is 1 then? Because this is a unit circle.
We have BE. That B 1.
That'd be 1. I didn't realize that it was Talk Like a Pirate's half birthday. I don't know. Anyways, I don't know. What do you call it when anyways? Okay.
And then BG is also 1 because that's also a radius.
Mm-hmm. It's another radius. Collectively, all radii. Sweet. All right. So we're starting to add things to this unit circle. We want to get some things that are always true. Can you give me an equation based on the triangle BCE?
BCE is we're going to have BC squared plus CE squared equals 1 squared, which is 1.
Sweet. Awesome. So can we introduce trigonometry into here somehow?
I think so, because since we're working with the unit circle, and we've been working with that a lot, we can define BC and CE in terms of theta.
We have our theta here. And what does that make, let's say, EC?
EC is the y coordinate.
Okay.
And so that's going to be sine of theta.
Sweet. So EC is, or CE, that's the reflexive property from a geometry, sine theta squared. And if you guys didn't notice, I'm going to write one more line. You'll notice when we write trig expressions and trig equations and all this stuff, if we square a trig function, we put the square before the theta. And that's to kind of not confuse us. If I were to put the square after the theta, is it the sine of theta squared? Or is it sine of theta all squared? So the way we deal with this is we put the square before the theta.
Reduce ambiguity.
That's a better way to put it. Thank you.
And then while you were talking, I just thought to myself, hey, well, if the y coordinate is sine, then the x coordinate is going to be cosine. So I wrote that in. And then, yeah, we can fill it in the exact same way. Fantastic.
Boom. And I think regardless of the value of theta, it's a right triangle, right? So regardless of the value of theta, cosine squared plus sine squared equals 1.
Is that an identity?
That is an identity. Regardless of the value that you plug into theta, that equation is going to be true. And if you think about it, if you take a number between 0 and 1 and you square it, and then you take another number between 0 and 1, you square it. If I'm kind of losing my words, but it makes sense that that's going to sum to 1. Cosine and sine are something between 0 and 1. So you're going to square both of them, add them, and then it's never going to surpass 1, is what I guess I'm trying to say. Sweet. So that is a Pythagorean identity. We've used in the Pythagorean theorem. Pythagorean identity. We got a lot more triangles in here. Let's try to label them.
So BDF.
BDF. Okay. Are you about to? Okay.
Well, I was just going to try to draw it with my triangle tool, but I forgot how to make it a right triangle. Shift. Aha.
Oh. Are you telling me that if I go,
So,
while you
boom.
do it, I'm going to show people what you're doing. Triangle, if you click the shift button, it makes it a right triangle. That is nice. So you have this red triangle. Beautiful. All right, we have one of the dimensions of this red triangle, right?
Yeah, we have the base is 1 because that lies on the radius of our unit circle.
Let me
We
convert
also
to
know
red.
that our angle EBD is, no, EBC is the same as the angle FBD.
Okay. Yeah, because they are what's the word? I guess reflexive once again comes in to save the day. They are the same angle. They're on top of each other. This angle is congruent to this angle, right? And they both share a right angle, right? So what does that make the triangle BEC and BFD?
They're similar, aren't they?
Right? Yeah. BEC is similar to, and I should put the triangle symbol, triangle. BEC is similar to BFD. What mathematical congruence do we get as a result of similar triangles?
We know that the ratio of their sides is the same.
So let's try to do that with a bunch of sides that we know.
So we know that BC over BD is going to be the same as BE over BF.
Yeah, BC over BD is equal to, what did you say? EC?
Yeah, EC, sure. over FD.
FD. Yeah. And just like redraw the triangle is really tiny. We have BC, we have BD, we have an F up here, and we have an E here. These two triangles are similar. And we know 3 of these 4 things. We know BC is cosine. We know BD is
1.
EC is
Sine.
And FD is what we're looking for. Moving things around, I believe we get FD is equal to sine over cosine.
Isn't that nice? Tangent?
That's tangent. FD, that's tangent theta. All right. That's kind of a coincidence. Tangent theta is the segment created by the angle theta that is tangent to the unit circle. That would make a lot of sense if that's the reason why they named it that. The tangent value is the length of the segment tangent to the unit circle. All right. What else can we get in this triangle? Can we get BF?
BF, I think so. Right, because that's the only thing that we don't know now that we know all the other sides.
So we got BF, and let's compare BF to BE. So BF over BE. BF over BE is equal to, what are you feeling?
Maybe FD over EC.
Tangent, or I guess I should actually write it, FD over EC. Cool. Right, BF is what we want. And BE is 1. FD is tangent. And EC is sine. What is BF equal to?
Tangent over sine, that's tangent, and I'm going to think, what is that? That's sine over cosine divided by sine is the same as 1 over cosine, which is secant.
We're using identities left and right here. BF is secant. And hopefully you recognize that BF, we're keeping it in red because we got a lot of overlapping stuff going on. All right. Do we have another Pythagorean identity?
I think so, because we have 1 squared plus tangent squared theta equals secant squared theta.
Oh, I'm actually going to go down to the next page because we have a spot here. What is this down here, this dot?
Oh, that's
yeah, that's for later.
That's for later.
Yeah. I thought you were grabbing me again. So we have sine squared plus cosine squared equals 1. And then we just identified that 1 squared, which I'm just writing as 1, plus tangent squared is equal to secant squared. Another identity, something that is always true. And then, yes, I'm running out a little. I'm going to get rid of the unit circle stuff up here just for the space.
Okay.
Let's just not forget that the unit circle is important. I think there's one more triangle in here.
Yeah, I think there is too. And I'm going to try to draw it with the triangle tool again. But this time I'm going with Yoda green.
Yoda green. Kermie green. Sweet.
And so for this one, we know the vertical side, BG. That's 1.
Well, before we do anything, this is a new triangle. Is it similar to the other two?
Yes. Why? Because it's a right triangle.
It's right.
And so we know that the angle on the bottom is going to be equal to the angle BEC.
BEC. This angle right here is equal to this angle right here. Nice. We have some like parallel lines going on here. That's like alternate interior angles or whatever. The geometry teachers would be mad at us for being so lackadaisical, but you know what?
It's okay.
It's chill. All right. So we have two similar triangles. We can now do the ratios. This is the triangles are like upside down though, so we got to be careful. Can you give me a ratio that's valid?
A ratio that's valid. Sorry, I was putting a theta in because it was bothering me.
I'm always skeptical. I'm like, is she crapping me later?
It's a really small theta.
Oh, that is a super duper small theta. Change it to like
I'm trying to make it bigger.
50 font.
50? I think 24.
24 is pretty nice. Okay, sweet. And then that is the same as theta because of AAA. Cool. There's a lot of ways you can think about these two triangles being similar. This is pi over 2 minus theta. This is pi over 2. So that needs to be theta. All right, we need a ratio. We need to find out what these segments actually are.
So GH over BC is going to be equal to...
Let's get the hypotenuse.
The hypotenuse. BH over BF.
So you've just jumped to the big red triangle.
Oh, you're right.
Are we comparing the Kermit frog with the blue triangle, green and blue, or green and red? I think either works.
Let's go.
I think since you said BC, I think we need to stick with the smallest triangle.
The smaller one.
Yeah, the one inside of the unit circle.
So that's what, EC? No, EB.
EB, yeah, the hypotenuse.
All right.
Boom, EB.
Ooh.
Math
Thanks
can be
for
exhausting.
helping me through that, Mr. Kirk. That was a really great way of giving me feedback when I was wrong.
Math can be exhausting.
Yeah.
And challenging. Okay, so we have a ratio that's true. One might call it an identity, but waka waka, to stick with the Kermit the Frog. Anyways, what are these values? GH, we don't know. BC, we do know.
BC is cosine.
So we have GH over cosine. And then BH. Oh, we don't know BH. Uh-oh. What should we do? EB is 1.
EB is 1.
So we have two ratios. GH over cosine theta and BH over 1. The thing is, we haven't used the one dimension in the green triangle that we actually know.
Which is?
GB, right?
GB.
What segment in the smallest triangle corresponds with BG?
EC.
EC. And we know both of those things. GB is 1 and EC is sine theta. So I think we can get BH and GH from this extended ratio.
Because then we can just say that BH is 1 over sine, which is cosecant. So BH is cosecant theta. And then GH is equal to cosine over sine, which is cotangent.
Wait, how'd you get GH? GH is equal to cosine over sine?
Cosine over sine.
Yeah. That you're using the first one and the third one, right?
Yep.
Cool. So that is equal to cotangent theta, which gives us this. Oh, cotangent theta is like the complementary tangent line.
Wild.
All right, so like all of these have meanings. So like the secant of the unit circle is the segment that is secant to the circle. If you guys remember what secant means in geometry, it's a segment that cuts a circle into two. There are many secant lines, like this would be a secant line. Actually, this would be a secant. A secant line would be a line. It would go through. But this segment here, HB, is a secant line. FD is tangent to the circle. The cotangent and the cosecant are just two other things that are secant and cotangent. Mr. Contreras, do you know why sine is called sine?
I do not.
So I need someone to fact check me, but I'm pretty sure, and I've said this for many years. So if I'm wrong, then I've told many not generations, but many classes of people the wrong thing. Sine, if you look at its etymology, it translates to bow. And if you kind of think about it, if I were to extend my arc here, let's go like with like purple, this arc here, and I were to extend my sine segment, it's almost like the bow of a bow and arrow. So I'm pretty sure that's why it's called sine. And so tangent, there's etymology there, but we know tangent in terms of geometry. Secant, we know that in terms of geometry. Sine is the kind of the odd one out there, but it's derived from the fact that we got a bow and arrow going on in this thing. What's the final Pythagorean identity?
I think it's going to be cotangent squared plus 1 is equal to cosecant squared.
Cotangent squared plus 1 is equal to cosecant squared. All right, 3 new identities, and these ones are not as easy to just internalize. Do you have a strategy?
I totally have a strategy because I never remember what the ones are that aren't the first one. So my strategy is I remember that sine squared plus cosine squared equals 1. That's what I store in my brain. And then I'm like, all right, let's divide everything by sine. Then, and I'm aiming for the last one now. So then sine squared over sine squared is 1. Cosine squared over sine squared is cotangent. And then 1 over sine squared is cosecant squared.
This is where you go, Mr. Kirk, why did you just make us do all of that geometry when we could have just taken the first one and divided it by sine squared?
No, but it was so fun because then we got to see the picture with the bow and we got to get excited about triangles. Like, it was nice.
I get really excited about triangles.
We can't do that every time because that's not practical.
Yeah. And then how do I get this second one then, if that got me the third one?
We'll take your first one, divide everything by cosine squared, and then you'll end up with 1 plus tangent squared, or well, it'll be tangent squared plus 1 equals secant squared.
Is it really that easy? Tangent.
It's so easy.
1. Oh my gosh. All right, everyone's allowed to be mad at me. I know no one's allowed to be mad at me. You learned the origins of the words, kind of.
Mm-hmm.
Do not claim to be a particularly large vocabulary person, but anyways, those are 3 new identities that we're gonna use, and we're gonna use them in just a second. But start to at least do this for us. Remember that one.
Yep.
And that'll be good for you because that comes up very often, very often. All right, let's use the identities. We now have, I said 20 at the beginning, now we have 23, and technically we have like 45 or something like that because we can move these things around. What's another identity that's true based on this first one?
Sine squared equals 1 minus cosine squared.
Oh my gosh, there's so many different identities that we have floating around here now that we've like opened up our mind to the Pythagorean identities. Right. So what do we use the identities for?
We're trying to simplify expressions, right? Like if we're given things that are looking not super easy to deal with, and we can simplify them using our identities. And any combination of them too.
So let's do that. We got secant theta over tangent theta. What should we do to simplify this thing?
Well, we could square everything and no, I'm just kidding.
No, don't do that. Let's not make it more complicated. Let's make it smaller, not bigger. This is not logarithms.
Well, secant is just 1 over cosine, and tangent is sine over cosine. Is there anything we can do with that?
Let me get a better color than like this, whatever that is, lavender. 1 over cosine theta, not better color, a more easy to see color. And then you said sine over cosine. So you've used your reciprocal identity, not inverse identity, and you've used your what is it called? Quotient identity. Cool.
Quotient identity. Yeah, quotient.
Yeah. So I call what you just did the Hail Mary move. The
Hail Murray move?
Oh, all right. Let's look at it. So I call what you do the Hail Mary move. You call it the Hail Mary move. And that's because you like, no matter what you end up given, cosine, tangent squared, this ridiculous thing, number 3 that we're going to get to in a second, number 4, you're always able to, at the end of the day, turn everything into the sines and cosines. And if there are any football fans out there, and I know there are some, you'll know that in football, it's at the end of the game, and you're down by 4, 5, 6 points, whatever. And there's like 3 seconds left on the clock. What do you do, Mrs. Contreras? You're 80 yards from the end zone to get any points. You can't kick a field goal. What do you do?
You tell your wide receiver, run as fast as you can, get in the end zone. I'm just going to chuck it. It's going to be great. And then it goes. And this past season in 2020 NFL, we had a wonderful example of a successful Hail Mary, and it was thrown by Kyler Murray. So it's now called the Hail Murray, and it's hilarious. That's Kyler Murray.
Let's look at this real quick.
Mr. Kirk.
Well, let's look at this. The Arizona's down by 4 points. Like, this is you're 4 points away. Even if you have the ability to kick a field goal is only worth 3 points in football everywhere. So what do? You step back and you throw it as far as you can. So Arizona down 4, 34 seconds to play.
He throws it.
Murray throws it. He's on the field right now. He has just thrown the ball however many yards. How many yards left? Doesn't matter. He's just thrown the ball into the air. And I believe he's realizing that Kyler Murray launched a 43-yard Hail Mary. And then here's his receiver, the guy in red.
Nice, DeAndre Hopkins.
Oh my gosh. 3 defenders still catches
Beautiful.
it. That is athleticism.
Call it in.
Hopkins somehow does this with not 1, not 2, but 3 defenders on him. And he holds onto it. I bet it's the gloves. Those gloves made her sticky. Let's see that in slow-mo. Let's see that from the side. Unbelievable. This is a Hail Mary. And this is, how do I go back? Alt-Tab?
Mm-hmm.
Come on. I think I'm just going to have to F11.
Tab. Control tab.
There we go. Right. I want you guys to try to use all the tools in your toolbox. We're getting all these identities. Look for them. That's what this is all about. Solving these problems is about honing your skills, manipulating and identifying and using the identities. So if you're just turning everything into sines and cosines every time, like, you're going to lose the game. You can't do a Hail Mary every single time. You're going to lose. But at the end of the game, or at the end of the problem, when you just don't know what to do, a Hail Mary is a cool move. So this is a long tangent to say it's totally fine, but do look for identities. We're going to do that in the next 3 problems. We're going to look for what we know, not just turn things into sines and cosines. What does this end up being now that we've done that, though?
That's just going to be 1 over sine.
Which I think we can get even more simple.
Cosecant.
Cosecant, yeah.
Can you full width that, Mr. Kirk?
I can. Thank you. Full width. Boom.
Love it.
Oh, that resolution is a little bit blurry. Anyways, this is the Hail Mary move. And you know what? When Hail Marys work, it feels really good. So I don't blame you if you want to, like, take something complicated, turn it into a bunch of sines and cosines and simplify. But the whole point, and you're missing the point if you don't do this, is to look for identities. So instead of turning into sines and cosines, which is tempting, Mrs. Contreras, what can we do here?
We can factor out a cosine because that's a GCF. So cosine of x can be factored out, and so we're left with 1 plus tangent squared x, which is one of our Pythagorean identities.
That is
secant squared.
Secant squared, yep. And the way I remember them is I got the sine squared, cosine squared equals 1, and I could do all the dividing, but I remember that the cos go with each other, and the not cos go with each other. The tangent and the secant go with each other. So this is going to be secant. It gets a little bit difficult when you start moving them around like we did in lavender up here. If that's not lavender, I'm going to get...
Minuses.
All right, so we got cosine x is equal to secant squared x. Cool.
But then secant squared is 1 over cosine squared. So then, like, or cosine and secant, one of the secants are going to cancel, and you're just left with secant.
Yeah, I don't need to write it the way I've just written it, but I kind of like to, because I like to really emphasize that cosecant and secant are reciprocals. They cancel each other out.
Pew, pew.
Pew, pew.
No, zoom, zoom.
Vroom. Chop chop.
Chop,
We
chop.
we need a verb for trig. What's it going to be? It could be like a bow and arrow. That's a lot of effort, though.
Yeah, it's a lot.
All right, there we go. We simplified it, and we didn't turn things into sines and cosines. So just keep that in mind. You're allowed to, but challenge yourself. All right.
So I have a question, Mr. Kirk.
Yeah.
Can we start on the right side of this and then make it into the left side?
Yeah. Well, so let me say one thing before I answer your question. And this is like almost a point of contention, but this is not an equation. This is an identity. Right? I am giving this to you and saying this is true. Prove it. Prove the identities are true. I'm not going to are true. I'm not going to give you something that's not true and say, prove it to me that's not true. Everything I give you when I say prove this identity is a true statement. And your job is to prove that it's true. So now, can you ask your question again?
So can I take the right side of this identity and then change it so it's equal to the left side of this identity?
Absolutely. If you want to, so our goal here is to manipulate one of the sides so that it becomes the other side. Whether that's left to right or right to left is fine. So if you want to manipulate cosecant, maybe multiply it by some stuff and get to the left-hand side, that's fine. I would argue that manipulating the left-hand side is going to be easier than manipulating the right-hand side. Because if I said, hey, turn that into this ridiculous thing, I wouldn't really know where to start. But if I say, hey, turn the left-hand side, this ridiculous thing, into something simple, then my mind goes, well, how can I simplify this? So with that said, how can I simplify the left-hand side?
Well, it looks like we have a 1, which I think we should leave alone for a little bit.
Maybe do something with it later. We could change it to sine squared plus cosine squared. Let's not do that.
That sounds like a lot. Maybe cosecant of pi over 2 minus theta, we can rewrite as its cofunction secant.
Okay, I like that idea. Boom.
And then the sine of negative theta plus tangent of negative theta. Well, those are both odd, so we can take those negatives out of inside the trig function. So we have negative sine theta.
Oh, minus.
Yeah, minus tangent of theta. And then I know that sine is in tangent as like a GCF that we could factor out. I guess we could take a negative sign out.
Yeah, let's take a negative sign out. I was going to say, should we turn that tangent into sines and cosines? Should we do like a mini Hail Mary? What would that be?
Or we can just use our brain and remember the quotient thing. And then treat tangent as sine times secant.
Mm-hmm. So I took the negative out. So we have sine theta plus tangent theta. Sorry for my inconsistency with parentheses. And you want to take a sign out of the bottom?
Yeah, factor out a sign in the denominator.
So I will say that this stuff is hard. Knowing what to do is tricky. Sine times 1 is sine.
Mm-hmm.
And then sine times secant. 1 over a cosine. Or secant. I like that better, yeah. That's the thing we have in the top. Oh, so were you looking to the future? Like you saw the numerator as 1 plus secant, so maybe like, let's try to make the bottom also 1 plus secant?
Yeah.
Look at what you have. It sounds like maybe that's not the case. Look at what you have and then see if you can generate that somehow. That's a really good tip. All right.
So now we have negative 1 over sine theta, which is
because
reciprocal of cosecant.
It's a lot of effort.
Gosh.
Which is negative cosecant, which is what we wanted to prove. Nice. What do you do when you've proven something?
You draw the little box.
Or you can write QED, or you can be fun and write IDI.
I did it?
Yep.
Okay.
Or my favorite is BGTD. I'll let everyone think about what that means. Anyways,
Okay.
So always put a box or a QED or a fun little acronym at the end to show that you've finished the proof. If you want to be like legit and professional, these are your way to go. If you want to be fun, these are the way to go. Or anything else you can think of. Let's do one more together. Hey, from here on out, I'm not going to put any more questions. This one is for the people that want to see another example. But all the questions will happen already. So if you're done, you feel really good, then you can call it quits here. But we'll do one last one. We don't want the videos to get too long. Is that cool with you, Mrs. Contreras?
Cool.
Sweet. Let's do this one.
Can we factor out a secant squared or a 2 secant squared? Is that going to help?
I think we can do that, but we can't do it out of everything, right?
No, but can we like do it in the parts? Because we can
factor by grouping. Yeah, jinx. All right, so I'm going to take a 2 out as well. So 2 secant squared x times what gives me 2 secant squared x? 1.
Plus, minus,
yeah. And what's the sine squared? And then as I go, I'm always just checking. Cool. Oh, the close parentheses there.
Isn't that's cosine squared?
Oh, we didn't do that one, but we can cosine squared theta is equal to 1 minus sine squared theta. That's just if we had subtracted the sine squared instead. That is cosine. Oh, nice. I was expecting a grab. I'm like on high alert today, if you haven't noticed.
Yeah, it's weird.
All right. Let's not forget to write everything that, like, we don't want to drop anything.
That's fair.
Okay.
And then, well, secant squared times cosine squared, those are reciprocals. So, pew pew.
Oh, true. So, pew pew. 2. Okay, cool. We have a minus sine squared. And I want to remind you about our goal. Our goal is to get 1. So if this is a 2, and our goal is to turn the whole thing into 1, what does that mean? This must be somehow.
We got to make that -1.
You got to make that -1 somehow.
Can we factor out a negative from the sine squared and cosine squared? I found one.
Oh, and the puns and the joke. It's too much today. We're on fire. All right. So 2 minus, we have our Pythagorean identity. That's 1.
Nice.
2 minus 1. That is 1.
7.
7?
No, it's 1.
It's 1? All I got to do is get, no, now it's just chaos.
It's ridiculous.
Boom. 1.
Nice.
All right. Trying to think of something profound. What would Gandalf say?
Right now?
About finishing something complete.
I don't know.
Like what did Frodo say when he threw the ring, or what did Samwise say when he threw the ring into the fiery pits of Mordor?
It's done. We said we didn't want the videos to get too long, Mr. Kirk.
Yeah, you're right. All right, let's close this one out. Yeah. Well, yeah.
What is happening?
All right, let's finish this thing up.
I don't know what that means.
Boom goes the dynamite. All right. I've stopped my share. We're done. Don't forget to drink your glass. If you finish that glass of water during the video, go grab another one. Any words of wisdom for us, Mrs. Contreras?
Don't end your proofs with boom goes the dynamite.
Don't? All right.
It's ridiculous.
All right, let's close. You send us out.